Hi, my dear friends. Hope you are doing well. My name is Anant, and I welcome you in the beautiful session of TOC. So, in this session, we are going to discuss how the finite automata and regular grammar are equivalent to each other. All right. So, as we all know, the languages accepted by the finite automata are called as the regular language, and from the regular language, by using the set theory like notations, we can generate the regular expressions with a specific format, right? So in the same way, we can, from the language, we can generate a regular grammar, all right? And all these four terms are equivalent to each other, my dear friends. Then only it is what we can say, all these things are equivalent to each other. So language can, finite automata can be converted into language can be converted into RE can be converted into language can be converted into finite automata, and regular language can be converted into grammar, and grammar can be converted into language. So up to now all these things we have seen, right? So now let's see how the automata can be converted into the grammar, and how the grammar can be converted into the finite automata. So this thing we are going to see in this FA and RG equivalent, right? So as we know a simple rule, so as we know a simple production rule that X gives Y, where X gives one non-terminal and Y gives one terminal non-terminal, or it may give one non-terminal terminal, or it may give only terminal, or it may give the epsilon, right? So let's apply the same rule of the production over here, and let's go with very simple example like A gives 0 A, and the same can be written as A gives A 0, and also we can write it like A gives only terminal 0 and A gives us epsilon, right? So these are the production rules, for example, and these can be divided into the two types, my dear friends. This can be divided into two types, my dear friends, of the grammar, and those are two types of the grammar are, one is your left linear grammar, it is called as, and other is the right linear grammar, right? So I repeat, the given grammar can be divided into two types of the grammar, right? One is the LLG and other is the RLG. So what do you mean by LLG is left linear grammar, and RLG is nothing but right linear grammar. So LLG is nothing but where the non-terminals are written onto the left side. Always the non-terminals are written onto the left side in the LLG, and in RLG the non-terminals are written onto the right side. So let's consider the same example here. So how this can be written as C? A gives, as it is LLG, non-terminals should be written onto the left side. A gives terminal, and A can be terminated by epsilon. And in the RLG, the non-terminal is written onto the right side. So 0 A gives me terminal, and A can be terminated by epsilon. So this is a simple, very simple difference between the RLG and the LG. So as a non-terminal is written onto the right side, it is called as RLG, and as the non-terminal is written onto the left side, it is called as LLG. That's very simple, right? So we can, the given finite automata can be converted into the RLG, and RLG can be converted into the given finite automata, and also the finite automata can be converted into the LLG, and LLG also can be converted into the finite automata. So these are two things we are going to see, my dear friends, one by one. So here in this session, we will focus on FA2 RLG. So this first part we shall cover in this session, and in the next session we shall cover this FA2 LLG and vice versa. So let's move ahead for converting the finite automata into the right linear grammar, that is RLG. Wow. So to do this, we are in need of some rules. So rules are in front of you, my dear friends, right? So three rules we do have. One is the FA and other is the RLG. So what this rule says, see, the X is transiting with input A to Y. Simple. So same can be written into the grammar as X gives A Y. Right. As it is RLG, so the non-terminal you can see here is written onto the right side. Simple rule. If X is transiting to Y, where Y is non-final state or any intermediate state with input symbol A, if it is so, how its grammar is written? RLG is written as X gives A Y. Let's see the second rule. X is transiting with input A to the state Y, where Y is final state. So if X is transiting to the final state with input A, so how it is written? See, X gives AY oblique A. And that's the rule, my dear friend. If I'm reaching to any final state, the same input I have to write it over there to terminate the grammar, right? Non-terminal. So this is the second rule you have to keep in your mind. Just we have to, while transiting, we have to check it out whether it is final state or not. If not, only we have to be limited up to this, like, and if it is final state, then we have to give a slash and a termination input symbol. And third rule is very simple. If this is a initial state that becomes the final state, all right, if the initial state is your final state, then you have to write X gives epsilon. That's it. So these are the three rules, my dear friends. Those are very simple, and with these three rules, let's move on to solve some examples, right? Simple examples. So you can see here a very simple example is given. First one, let's give a try to solve the first example. So you can see Q0 is transiting to Q1, where Q1 is the final state and the input symbol is A, and here the input symbol you can see is B, right? So simple rule is that let's consider this Q0 as an yes and Q1 as an T. Now we have to convert it into the grammar. So we know very well the type of the non-terminals which we are using in the grammar are like yes, T, P, Q, and so on, right? So for better understanding, let's consider this Q0 as an yes, and let's consider Q1 as an T. So by replacing what diagram we will get, see, here I will get yes, and as this is the final state, let's call T A and B. Very simple, right? So now how I can write it over here is yes gives, right? Input symbol is A, and I have to write the non-terminal onto the right side as it is RLG. So it is transiting to T, and as it is transiting to the final state, we have to terminate it by the input symbol. Simple. So this is a production rule for A. Now let's try to write the production rule for T. So T, if you see, is transiting to itself with input B. And as it is final state, we have to write it like B T terminated by B. So this is an grammar for a given finite automata. That's very simple, my dear friend, right? So just what we have to do is we have to consider the number of states present into the finite automata, that many non-terminals should be there in our grammar part. So let's move on to the second example, where again the concepts will be clear. So it's like similar to the first one only. So let's consider again a Q0 as an yes and Q1 as an T. So let's call Q0 as yes and Q1 as T. So now see how this can be written as. So I will try to write the production rule for yes. So yes is transiting to itself first, right? So what I will write it here, A yes, and as it is non-final state, not necessary to write with slash and so on. And let's try to write the another production rule for yes with other input symbol, my dear friends, right? So that's a very good practice to write different product rules for different input symbols. So as this was input symbol A, we have written for A. Now let's try to write for B. So Q0 is transiting to Q1 with input symbol B. So this is your B and it is transiting to T, and as this is your final state, we have to terminate it with V. So these are the two production rules for yes with input symbols A and B, right? So now let's try to write for the state Q1, where we have represented by T. So T is transiting to itself. So A, T, A, and again T is transiting for the another input symbol B, T, B will be the grammar for this. So these are the four production rules for four input symbols, including two states in a given finite automata. So I hope you people are understanding this, right? So this was all about when the finite automata consists only two states. Now let's move on to a third finite automata which consists of three states, my dear friends, right? So any nothing rocket science in this part, my dear friends, in the conversion of the FA to RG and RG to FA. That's very simple and you can score out of 4 marks, right? So let's give a try to this. Now let's call Q0 as yes, Q1 as T, and Q2 as P. All right. So three non-terminals I can have in my grammar. So I will start from yes first. So yes, you can see here. So I will name it here as T and P. So yes is transiting with A to Q1, and yes is transiting to Q0 itself. Yes itself with input symbol B. So I will write it here for B, yes. So this is my first production rule. For the yes with input symbol A, it is transiting to Q1 in the sense that T, and as it is non-final state, I will stop at AT only. So I will move on to the state Q1, which I had given it as an T. So T goes to T itself with B, and T goes to T goes to Q2, that is Q1 is transiting to Q2 with input symbol A, and as Q2 is the final state, my dear friends. So how this can be written as C? It can be written as A P slash A, right? So these are the two input symbols for the grammar T. Now I can write it for the Q2. So I can write here by making this division line. So I will say P gives. So Q2 is a transiting to Q1 with A. So I can write it like A, Q1 is represented by T, right? And the next and the last one is P goes to P with input B, right? But it is final state, that's why B. So these are the total 6 production rules for 3 states in a given finite automata. All right, I think you people are understanding this, my dear friends. So let's move on to the last example where the finite automata consists of the 4 states you can see, and already in the problem statement they have given the grammar part also, where the Q0 is represented by S, Q1 is represented by T, Q2 is represented by P, and Q3 is represented by Q. So Q0, Q1, Q2, Q3 are represented by S, T, P, Q. So these are the 4 non-terminals in my finite automata. So let's start one by one. So I will start it from the yes, and if I keenly observe, yes is the transiting to Q1 and as well as it transiting to Q2. So I can write yes is transiting with input symbol 1 to T, and it is non-final, that's why I can stop here. So for the next production rule of yes is with 0 it is moving to Q2, that is P, and as it is also and non-final state. So this is the final state is Q3, my dear friends here. So just make a simple change. Q3 is the final state. So these are the two production rules for yes, and then after that let's move on to T. So now T gives by 0 it is transiting to Q3, that is Q, and Q is the final state, so slash 0. T is also transiting to Q0, that is with 1 it is going to yes, right? So I will write for Q2, that is P. P is transiting to Q0 with 0, so I can write it like this. And the second production rule for the P is it is transiting to Q with 1, and as it is final state I have to write no 1 sorry, right? So lastly let's try it for the Q, my dear friends. So Q is transiting to P with input symbol 1, and Q is transiting to Q1, that is T with 0. So these are the 6 plus 2, total 8 production rules of the 4 states in a given finite automata, my dear friends. So hope you people are understanding this. So this is all about how to convert a given finite automata into a RLG, that is right linear grammar. So let's move ahead to see how to convert a given RLG into a finite automata. So again, so let's see how the RLG can be converted into the finite automata. So this will be a given grammar to us, my dear friends, and from this then we can identify thus how many non-terminals are there, right? So as A and B, these are the two non-terminals, in the sense two states are going to be there in my finite automata. So just I will tell the first production rule to you people is like, so just I will tell you people the first production rule. See how it is. A gives us AB in the sense AE is a transiting to state B with input symbol A. In the same way, all these terms are. Now just see how I will draw this. It's very simple actually. So always I have to start with first production rule, and that is A will be my initial state, right? And A is going to be, and B is A is transiting to B with input symbol A. And that's very simple, my dear friends, right? So this completes the first production rule. The second production rule is B gives me B, B. So B has a self loop with input B, and B is transiting to A with input B. Simple. Now see this production rule. Whenever a non-terminal is giving only a single terminal, it means that this is our final state. So B goes to some state which will be my final state with input A. Now let's call this final state as an F, or any non-terminal you can give over there. So this is a simple finite automata how I can get from the RLG. Let's move on to the second example where the grammar is given. If you see here, the how many non-terminals are C? 1, 2, and 3 non-terminals are there. In the sense, 3 states are going to be there in my finite automata. So let's start from the initial state. Initial state, let's call it as an yes, my initial state, and yes is transiting to B with input B. Simple. Let's move on to the second production rule. See, B is transiting to C with input B, and as slash B is given here, it means that my C is the final state. All right. So B is transiting to C, which is my final state C with input B, right? So this is the second production rule. Third production rule is that B is transiting to B with input A. The simple as it is, right? And then finally again C is going to only A, and as I just now told you that if any non-terminal is going to a single terminal, it means that it is the final state. So what I can write it here is that C is moving to one more final state, my dear friends. So I may call it as an F and with input A. So in this finite automata, I do have two final states and two non-final states. So initial state, this is my intermediate state, and these are the two final states, right? So let's move on with the simple example where S gives me 0 yes 1 S epsilon, right? So here the yes is giving me, yes is a simple state, and it is going to 0 yes and 1 yes, right? And I also, yes is giving epsilon. Whenever it is giving epsilon, the initial state is my final state, my dear friends, and this state is giving me 0 and 1. So any number of combination of 0 and 1 can be formed by using this. So a simple finite automata for a given gram. So these are the three examples, my dear friends, from the given RLG, how we can convert it into the finite automata. So I hope you people are understanding this. If you have any doubts, debates, discussions, please put it in the comment box. So thank you so much.